what we want to be able to do in APL is search through text and either return that text or the position of the text or modify the text. So what I discovered was that there's a couple of idioms. If we've got that value in a variable, we named that text, we can already do that. That gives us the positions of the single character A within the text. And you will notice that there are other quad IO options which you can choose. Similarly, if we want to find longer character vectors, we've got find. So that has found the one less character because the A at the beginning is not followed by a T. And we can modify text with something like that. So there we are, thank you. You've been a great audience, thank you very much. Now clearly that's not enough. The problem is that the things that we're looking for are very definite literals. We want to be a bit fuzzier. So, if we wanted to look for that, well, we can do that with find already. But what if we wanted to find any postcode? That's a UK postcode, I should have said. Any postcode. So we want to find 2 characters, 2 numbers, a space, a number, and 2 letters. Well, that's a bit more difficult, but it's even more difficult when you realise that postcodes can also look like that. There's 2 letters, only 1 number now. Or they can look like that. So we've only got 1 letter, and we've got 2 numbers. We could have 1 number as well. And they can also look like that. There's an extra letter after the first number. And as a slight diversion, just in case you're interested, the first one was the Bramley office. The RG is the postal district, that's Reading. The second one is Heathrow Airport. The second one is the BBC Studios in Manchester. And I suspect that there might be people here who know what the last one is. Does anyone know what that is? It's Buckingham Palace, that one. London South West one. Anyway, so what we really want is to be able to look for any postcode in some text is to be able to say that we want 1 or 2 letters, we want 1 or 2 digits, then we want 0 or 1 letters, which covers the last one. Then there's got to be an explicit space and 1 digit and 2 letters. So that's quite a complicated thing to be able to construct a phrase to search for, but in fact with regular expressions we can express that very easily. So that's what we're looking for. Now we can say 1 or 2 letters, just like that. In the first bit there, in the square brackets, there is a class, A to Z. That means that any single letter between A and Z will match. And then we qualify it in the braces there with saying 1 to 2. There can be either 1 or 2 of them. And similarly for the numbers. And then similarly for 0 or 1 letters. And then for a space, we actually write a space, which wouldn't be very interesting if I didn't do that, so you can actually see there's 1 there. And then for the last bit, 1 digit, there's no qualifier for the numbers there because that implies 1, and then 2 letters. Now, that is actually slightly more verbose than it needs to be, but for the sake of simplicity, I shall keep it like that. So our regular expression to say that should match any postcode looks like that. That's how we can express what we want. I should say that I'm showing you throughout this session some examples of regular expression syntax, but they're really just teasers. This isn't really what the expression's about. The session's about. It's about how we put it into the APL interpreter. So you'll see some tantalising examples, and if you're interested, then we can investigate them more another time. Oh, demonstration. Hang on, I've got to do something. Okay, so this demonstration is to show you what other languages which already support regular expressions are doing, to give us some ideas of what we might want. Now, work. Here we go. So, I have a file on this computer which has got text in it. It's standard lorem ipsum text. Cat just shows me what's in this file. it's just a load of random text, but you'll see that in there I've snuck in a few postcodes. There's one of them. There's one of them. I don't think I can reach anymore. Oh, there's one up there. And there's the other one. And it's kind of interesting that those are both on the same line. We shall see why in a minute. Okay, so that's the file. We haven't done anything with them yet. So we have a utility called grep. Grep searches any stream of data, and the file is the stream that I'm going to use this time. And there you can see, well, you can see almost the irregular expression I gave you. The Unix shell gets in the way here, and I have to escape some of the characters which otherwise the shell would interpret. But it is otherwise the same regular expression. And what grep does is it gives me only the lines in the file that match that expression. So you'll see that all I've got now are the lines that have postcodes on them. So that's quite a useful thing to be able to do. But grep can only do that. It's pretty useless for anything else. Here we've got another utility which also works on a file. It's called sed, which means stream editor. And instead of finding things, now we've got, I'll use the mouse. We've got the regular expression as before, which is all of, no, it's not. That was a bad idea. We've got the regular expression as before, but at the end, we've got what we're to do with it. Now the /0 there means give me whatever you matched against, and the brackets around it mean put it in brackets. So when I run that, which hopefully I still will be able to, yep, you can see now that the file has been modified and all the 4 postcodes are now in brackets. So there's a very simple replace that took place on that file. This one, well, we've got a little loop going here because there's several different postcodes, but you'll notice that I've introduced a 5th one, and this 5th one is not valid. It runs around in the loop, and it's basically saying if it matches this pattern, if it's a valid postcode, then display it, otherwise we don't do anything. So when we run this, we should see the 4 valid postcodes. But the interesting bit in the bash shell script is this first line, which is basically saying, does that thing presented to me match the regular expression? And that's a very useful thing to be able to do. And then there are languages such as Perl, which have got this built in, and Perl is very powerful with them. It can do a number of things. I'm only showing one example. I'm doing a substitution like with sed. So again, I'm going to put brackets around anything which matches a valid postcode, and I'm passing it a string which includes several valid postcodes and one that's not. So when you run that, it doesn't parenthesize the last one. And finally, and this is particularly useful, if I've got a file, this is the VI editor I've got. I can now use regular expressions to search and replace my source file. Now, this is a pretty stupid piece of C code. Ignore the first 2 lines there to make my life easier.
You can't read them anyway.
Good. I was going to plug a mouse in. Do you don't mind what I do? I think if I do, it won't pick it up in time anyway, will it? No. I'm not going to bother. This little C program, which as I say is stupid, has got in it a variable called mon, which is short for month. And I don't like that. I want to change that variable to be called month. So if this is going to work. I do need to have the mouse on the phone. No, I can type it. Right. 3, hold up. So what that's basically saying is from lines 3 to the end, I've selected lines 3 because my useful little comments are at the start and I don't want to affect those. Search for the string mon and replace it with month. There's no actual regular expression there. It's going to be a fairly simple replacement. But you might be able to predict that it's not going to work because earlier up in the program I've got a variable, I've got a name Monday, and I don't want that to become month day, but it will do. So that wasn't good. But regular expressions allow me to do clever things. And if I say 3, $S. Now, special character. In VI it's slightly different to anything else, but if I slash less than means I've got to anchor against the beginning of a word. This will only match.
You said slash less than and you type less than slash.
Backslash less than, not less than.
Yep. Thank you very much. So now I've got this pattern will only match if it's anchored against the beginning of a word, which means that it wouldn't match if there was a word character such as a letter or an underscore or a number immediately before it. I can look for mon, and I can do the same at the other end. So it's got to match also be anchored against the end of a word, and I can replace that with month. And that means that Monday will not match. So now I've refactored my source code and it has worked. Excellent. Right. So those are useful things I think would be nice to be able to do. So let's see more about regular expression support. We use it for the basis of search and replace. Some of those examples just searched, others, when they found things, they did a replacement of some kind. And we find them increasingly in other languages. People make great use of them. Well, I think we could make use of them in APL. And I also think that newcomers to the language might expect it to be there. And if it's not there, it might be a barrier to them. Now, luckily, there's already a freely available a library out there called PCRE, which stands for Perl Compatible Regular Expressions, which does the core of the work for searches. So we can build this into the interpreter relatively easily. I would say that the library does about 90% of the work, but in fact, we have, within Dyalog, spent so long trying to design this, we've probably only done 50, but either way, it's done a great deal of it. So what I want to talk to you at this stage is what design we came up with and why. Please stop me if you want to ask any questions. Right, so I should clarify that we haven't yet finished. Everything that I show you now could be completely different by the time we release this. It is still under discussion. But we absolutely want to produce something which is general purpose. Part of the reason for showing you those other examples was that there was lots of tools that did different things. No one tool was particularly good at everything. We want to be as good as everything without having to introduce loads of new features, just one. So the first thing we had to consider was the source text. This is something that's going to work on text. It's going to search through text. What it does with that text, there are many things it might do, but it's going to work with source text. We've got to decide what form that could take. So we have this idea that the thing that we want to operate on is a document. Now, we reckon that you might want to store a document in a character vector. Now, if it's a huge piece of text, a book, it might still be a single character vector. It could contain embedded new lines and so on. But that's a valid way of having it in your workspace. You might also want to work on a vector of character vectors, where each character vector represents one line. There's an implicit line ending between them. And wouldn't it be nice if you could work directly on files or other streams? One advantage of that, if we can search and filter like the grep tool did, we might be able to process large files without having to read them all into the workspace. Other things we considered were a character matrix. In fact, early implementations did support those, but there wasn't much advantage in that, and they caused all sorts of problems, such as, because they have lines at the end, do you trim the spaces at the end of the lines, do you trim those? When you generate a matrix, you put in extra spaces at the end of lines, so you've done transformations that you never asked for. So in the end, we decided, no, they're just too much trouble. We don't want to support nested arrays. I can't imagine what sort of document they would represent or how we would process those. And this is very much for text only, so anything with numbers in, we're not interested in. So as I said, if you've got a document that contains lots of lines, it might be represented with embedded character terms, and it might be a vector of character vectors. But there's also consideration of how you process it. That tool grep that I showed you at the beginning processed line by line. Any line that contained that a match was found got through to the outside, but all the other lines were dropped. So do we want to process our documents line by line or entirely, in their entirety? And I think the answer to that is that we want to do both, because there's advantages to both. If it's line by line, we use far less memory. We only have to work on a single line at a time rather than the whole thing. And there are semantics to that which are very useful. You saw the grep example. You can also say that you want to modify or search for only the first item, and you might want to actually mean the first item on any line. If you do the entire document, it means that you can construct searches which go across lines, which you couldn't do otherwise. And if you replace a line with nothing, you can remove it completely, whereas all you could do is turn a line down to 0 length if you process line by line. So that was our first consideration. We had to be able to do both of those. And one major design decision which we argued over was, well, we can represent the document in two different ways. Should that not dictate how we process it? And the view at the moment, subject to change, is that the two input document formats are effectively for the same thing. So they are interchangeable, and therefore they shouldn't dictate how the file is processed. Now, once you've found stuff, you have to do transformations of some kind. Those traditional tools that I showed you use a character vector for the transformation, very similar to the search patterns, the irregular expressions. So there is, if the /b red /b says that any word delimited occurrence of red is replaced by, in a replace operation, is replaced by the word blue. This is saying that the period there is saying match any character. It's parenthesized, so that turns it into a group, which you'll see why in a minute. Then you've got any character AT. If it finds any character by AT, the transformation is /1. /1 is the contents of the first group. So that, if it encountered the word cat, would give you the C, but not the AT. So that's useful. But we think that we want something more powerful than that. What if we could use a function? So this, I like this one, this regular expression looks for the characters DM space. So this is for currency. We're looking for Deutschmarks. Now, the /D is a shorthand for the single digit that we had before as 0 to 9 in square brackets. So, and then the plus is a shorthand for braces 1, comma. In other words, we've got to find one or more digits, and now we've got another group in the parentheses. Let me point those out. That parenthesis and that parenthesis are forming a group, and within the group there is a period which is escape. That doesn't mean any character, that really means a period. And then we're looking for digits occurring 0, 1 or 2 times. And then that group itself has got a question mark after it, which means that it can occur 0 or 1 times. It's optional. So that should find anything that looks like a price, a numeric value with Deutsch BM in front of it, a currency amount. And once we found it, why don't we do that transformation? So it's a defun. You've seen what those are from the previous presentation. Don't think too hard about omega.match at the moment, but that is the text it matched. Whatever matched that original pattern comes into this defun as omega.match. If we drop the first 3 characters, we're dropping the DM space, so we're just left with the numeric part. We evaluate that to give us a numeric value, We multiply it by that number there, which is the exchange rate between Deutschmarks and euros. We format that to turn it back into text, and we stick a euro in front of it. So if we've got any document that's full of values, quantities in Deutschmarks, that will automatically turn it into euros. And finally, we've got numeric codes. You saw the first APL examples. They gave us like positions of where things were. Well, it'd be very handy to have a shorthand to say, I want to know where these matches were. So we have codes that mean where they were, where the match was, which line it was found on, how long it was, and which pattern it matched, because we support multiple search patterns, as you'll see in a minute. So now that we've got our requirements, we know that it has to be an operator because we can invoke functions. We think it has to be a system operator and not a primitive because it only operates on certain types of data. It has to have a name, so it begins with quad because it's a system operator, but the characters that follow that are not as straightforward as you might think. We've changed our mind over this many times. We started off by thinking about, well, it's a regular expression handler, so it could be regx, or it could be reg, or it could be rx, which is what we settled on for a long time. And then we thought, it's rather annoying that one function is doing both search and replace, and we have to keep qualifying with an option which one. So we need separate ones. So is it search, is it replace, is it search, is it ripple, is it actually search, or is it a find? Is it a replace or something else? So you would not believe how long we spoke about that. But in the end, we decided we'd just call it quad R and quad S. So we have arguments and operands to fit in this operator. If it's quad R, we can put the regular expression itself on one side, the transformation on the other. Because the transformation can be a function, we have to keep those separate. And that's our derived function, which does a replace operation. And then you apply that to the document in whatever form it is. And as I said at the beginning, we might like to operate on streams, which means we might want to output to stream. So in that form, its output is the result of this function. But if you give it a stream, it will write to the stream instead of generating a result. And the problem with that is that we might want some options, for example, whether the search is case sensitive or not, and we seem to have run out of space for them. So a slight diversion. We want that. There's nowhere left, I've said all that. I should also say there's no correct place for options. The reason, what I mean by that is that some options, for example, whether the search is case insensitive or not, are part of the search itself. They're almost a feature of the regular expression. So you would want to stick the options in there somewhere. However, other options, for example, whether a stream is encoded in UTF-8 or UTF-16, are not part of that. You want them to be here somewhere. So not only is there nowhere for them, there's nowhere to put them. I don't know how that happened, but that's handy. So this is the diversion. Ken Iverson proposed variant many years ago. Nobody's implemented it. We're talking about it now for various things, and this is one place where we might use it. It modifies a function, so that, as you know, will generate either 0, 1 or 2, or 1, 2 or 3, depending on your preference. If you could write that, which you can't, but if you could, we're saying that it's a variant of iota which has got a neg1 index origin, so that would generate neg1, 0, 1. Now, for the purpose of what we're doing, I've spelt variant as quad opt. There are various reasons for that, and we may or may not stay with that permanently. So, in my examples, that's what I'm going to use. That's what we've currently implemented. Now, I have to say, this within Dyalog, we are in various minds about this, various different opinions from different people. So, what you see today may not be whatever gets out, but I'm hoping it will be as I show it you now. So, if you have that derived function, that function will search, well, I've shown you that one before, it will search for any character AT, give you back that any character. So if I apply it to that text, I get the S and the M, but not the capital C at the beginning of cat, because I put that in uppercase. Whereas I could modify the function using an option to set ignore case, and now I get the capital C as well. So there I named the derived function and I used the operator on that. This time I could create another named function which includes the option. So if I run that on the same text, I get the same results. And I could do the same thing again. I could modify that with another option to set another option value. So on that I've got both ignore case and the in-file encoding set. Right, more demonstrations. So let's play with it. So this really is hopefully just to whet your appetite. I didn't really say much about what the difference between search and replace is, so I put it here really just to show you. In this case, I've got the text, the quick brown fox, etc. What I'm searching for is any vowel. That's the square brackets say that it is a class. The class is of the characters A, E, I, O, U, and I'm going to replace them with something. And what I'm replacing them with is the thing that it matched, /0, which is modified to uppercase. So if I run that, it substitutes all the vowels with their uppercase equivalent. In search, I get each match come back to me in a vector. So again, whatever is matched is modified to uppercase, but instead of being substituted back into the input text, I get a vector of those letters. And in search, you don't, because you're returning a vector of things, it doesn't have to be text. It's not going to be substituted back into the original. So it could be anything. And of course, then we've got what we saw earlier on. There's code. I was hoping that I wouldn't have to do that because I know that this will go wrong if I increase the font size. But if you can't see it, I will try.
Oh, go, come closer.
Is everybody at the back having trouble with the size?
Why is it going to go wrong?
Because when I bring up some of these lines, you won't see all of them. I'll have to scroll back and forth. All right, okay, you took me into it. That's the wrong way. Is that big enough? Better? Okay. So the code 0 says, tell me whereabouts you found the match. When I run that, I get the actual positions of them. Okay, so you saw when I did the examples with the other tools and utilities, the first thing I did was I dumped out the contents of a file for you to see all of it. So let's do the same thing here. We haven't really finalised what we're going to do with streams. At the moment it operates on a tied native file. So that's the tied native file. I'm going to just do a null substitution on it. I'm going to search for nothing and replace it with nothing. And then you can see at the end I'm mixing it. That's simply so that I get back not a vector of character vectors but a matrix, because that will display better on the screen. So that's the entire file, just to show that we're working on the same data. And arguably we might want to optimise that, because if people tend to do that in order to read in files, we don't want to actually go through the search engine. So watch carefully this, there's a mistake, see if you can spot it. This is grep. Grep was the thing that extracted certain lines from a file and threw away everything else. So we're just going to look for these lines that got the postcodes on. Because this is a tied native file, I've now read it, so I've got to see it back to the beginning, which is a bit of a fudge. Here we go, I'm looking, it's the same search pattern as before. There's the postcode. I'm doing a search, and then the transformation is to give me the entire line on which the search was found. And as you can see, it sort of worked, but I've got the last line twice. And the reason I've got the last line twice is because it's got two postcodes on it. So there is an option, so you'll see an option running, which will fix that. Let's go back to the beginning. Here I've set quad opt match limit 1, which means that only give me the first match on every line. So when I run that, I get the result I'm looking for. Oop, that's an instruction to me. Okay. I assert that here there is not a file called x.txt. Do you believe me? Right, okay. So now if I create a file, using quad n files as well, sets back to the beginning of the input file, I can send that same output, that same result as before, to the output file by putting the additional option at the beginning. And hopefully I'm going to untie it. Yep. If we look now, there's the file, and it's got the right results in it. And as you gather, we're going through all the original tools. Yep, I'm fed up with reading this file, so I'm just going to read them into a variable. So I've got the variable ipsum with that text in it now. As you can see, it's got it in. I'll get rid of the input file, put the pattern in another variable, or name it. So we've done a grep. We can, rather than just give the lines, we can get the positions within the file. So that's line 2, column 7 with quad IO0, line 7, column 34, and so on. Compare and contrast with this, where I'm saying to process, by default it's processing line by line. This is saying process the entire document at once. And as a result, everything's on line 0. Or in block 0 now, and those are the offsets within the entire document where it's finding the postcodes. Here's sed, which is changing things within it. So search the pattern, replace with paren, and then the match. And you see that we've got brackets around the postcodes, like sed example did. And in the bash shell script, we wanted to say, is this a postcode? Well, we can just check the length of the result. If there's no match, if there is a match, that will be non-zero. If there's no match, that will be 0. So we can now use that to tell whether or not it matches. And Perl modified string, there it is, character vector with postcodes in. Search the pattern, very similar to the last one, put brackets around it. It's equivalent to Perl. What are we doing? We've got plenty of time actually. And I'm avoiding VI because that's actually far more complicated than you might think. So I will come back to that at the end of the demonstration. Okay, so I showed you at the very beginning using find. On that text, there's the find example. There's the exact equivalent using a regular expression. Well, what am I doing with that? Oh yes, so here we go. We've got those word delimiters, so we don't want to find the letters RED inside of words. We can put /b in beginning and end. Those are boundaries between words. And you'll see that this changes the word red into red, but it leaves the RED inside incredible left alone. And we can have multiple patterns. So if we wanted to change red into blue and green into yellow, we could run quad R twice. So our input text is red and green. First thing we do is we change the red into blue, and then we pass that through to another one. We pass green into yellow. We change green into yellow, which gives us blue and yellow, as we might expect. Let's try another example. We've got red and blue. We're going to turn red into blue, and then we'll turn blue into red. So we should get blue and red come out. But of course we don't, because the first replace turned the first red into blue, so we now have blue and blue, and then the second one turned both of those blues back into red. But we have an option of putting multiple search patterns in quad R, and they pair. Either there's multiple to one, or there's multiple to multiple, and they pair. So red turns into blue, and blue turns into red. I should show you a bit more about the groups. So this search pattern looks for a single word character /W. It's grouped, so that's the first group. It looks for 0 or more word characters. The star means 0 or more. That's group 2. /1 says give us group 1, and I'm passing that to the original text ipsum. So that gives us the first letter of every word. This one's quite interesting. This time I'm using the group and the search pattern itself. I say give me a word character, give me 0 or more word characters, give me whatever you first matched, the first word character. The whole thing's got to be delimited by non-word characters, and then if that matches anything, give me the whole thing. So that will find all the words that begin and end in the same letter. And there's some examples of transformation functions instead of the strings, and I'm going to go off on a tangent, I think. Have I got time? Yes, just. Okay. A few years ago, I was in an interview, and the interviewer just suddenly sprung a question on me. It was for a low-level C coding job. He told me that I had in memory an arbitrarily long sentence, and I should reverse all the words within that sentence. So the quick brown fox would turn into fox brown quick the. And there was I in a panic. I was trying all sorts of things. Well, I could compress that data because I'm not using the full 8 bits for all those characters. And then suddenly it occurred to me what you have to do. So there's my text. If I take the first T and put it and swap it with the last G, and then take the second letter and swap it with the penultimate one, and so on, I reverse everything. Well, I've got the words in the reverse order, but I've also got the words themselves in the reverse order. So now what I need to do is to swap the G and the D in the first one, the Y with the L in the second one, and the Z in the A, and I'll put them all back again. So if I reverse my text and then identify all the words and reverse them, I reverse all the words in the sentence. And there, the interesting bit there is I'm using a defun, and again, the thing that matched, I'm just reversing it. So I managed to figure it out eventually. I was told later on that no one else previously had, which I found extremely surprising. And I got the job offer, which was great, except that then I saw Morton a couple of days later, and I decided I'd come and work for him instead. Now, I've shown you before this omega.match, and I said don't worry about it too much now. What we get to this function is a namespace. And what I'm going to do here is I'm just going to look for the fox so I get one match, and I'm going to dump out quad NL2 on that namespace so you can see what's in it. These are in alphabetical order, they're not very useful in that order. Let's start with match, which I've seen. That's the entire thing which matched. And then we've got lengths and offsets. That is the offset is whereabouts the match was. The length is how long it was, and that is a vector. There's the match itself, which is \0 when I've referred to it in transformation strings. Then if there's another value, it's the first group, and so on. The pattern that matched, because I could have multiple patterns, and the number of the pattern. The block, which is either the entire, it's either going to be the entire thing if I was in line, if I was not in line mode. Otherwise, it would be the line. Otherwise. The block number, or the line number. What else have we got? A little flag to say whether or not we're working in replace or search mode, and almost equivalent whether or not it can only return text, because in replace mode you can only generate text. It would be an error if you did something else. In search mode you can return anything, except if you're writing to a stream. You can only write text out. So let's do that Euro conversion, Deutschmark conversion we saw before. So there's the text. There's the search I showed you before, which I won't go into again. But you can see it's done the conversion. It's done it, but it's possibly not done quite what we wanted with all those decimal values. So hold that thought a minute. Let's generate another function which simply truncates. It's not a very good way of fixing this, but it will illustrate a point. I'm going to search for 5 characters and then in a group and then another character. So this will only match 6 or more characters, and it will return the first 5. If this fails to match anything, it will just return what it was given. So I'm hurrying up because I can see the time's cracking on. If I trunk my text, it's just give me the first 5 characters. So I'm going to show you using that in the function I had before. It's given me much better looking text. And the thing that's happened there is that this quad r, the outermost quad r, has called this function, and whilst that's still running, it's called quad r again. So just to say, you can nest this as deep as you like. We could name that, and then we can apply that function to the text directly. We can use traditional functions. So there's the same thing as a traditional function. And there I am using that one instead. Now here comes the fun bit. This is the bit I said I would come back to. That's the same function I just showed you. If I do quad CR on it, I get it come out as a matrix. So if I split it, I get a vector of character vectors, and now I can process that with quad R. So if I replace the characters of in with search res, I'm going to rename that parameter. Is that right? And then finally turn it back into a matrix and fix it. You'll see now that I've renamed the parameter in this function. So that's useful, and that's the start of what we saw in VI. Go away. There we go. Good. That's that done. I'm going to skip this screen because it's not very relevant and we're running out of time. This needs to apply. I just showed you processing APL source. So there, if I was to take my function f, turn it into a matrix, split it, search for every occurrence of end, replace it with x, y, z, refix it, that would work if I gave it that line. That's good. But unfortunately, it wouldn't work for all of those examples. It would mess up that word tender, it would mess up that delta end, it would mess up that colon end, and it would mess up the contents of that string, that character literal. So we need something better. And at the moment, the standard PCRE engine doesn't give us what we need, because APL source has really weird character classes. The word character, which we saw be using a lot in previous examples, would not apply for APL source. So /w, the word character, could be replaced exactly with that. For APL, supposing we had something like \iota, it would be equivalent to that. Now we could, within the interpreter, support that simply by doing that substitution in any character, in any patterns that you gave it. So that would be quite useful. But it still wouldn't be enough. Here's something which, right, let's have a look. It's looking for any APL word, so that it's going to split the entire document up into words, and then it's in the function it says, if that word is end, turn it into x, y, z. So that's quite handy. And all of those are now correct. It will see tender as one thing, and it won't match end, and so it won't change it. But it still gets those two wrong. So our task, it gets that one wrong because of the way that you can say an APL one end without a space between them. Quad CR will never generate that at the moment, so it might not be an issue. So there is one of the things in the paper I asked for, when we get this up and running, I think that we need to start thinking about this, and we will really appreciate any feedback, whether or not that's important, and then how we might go ahead and do it, what we need to add to support APL. So quick summary, questions if we need them. We think that these regular expressions give a very powerful text search and replace. They make them more appealing to everybody, but we think we need them for newcomers. This variant operator is probably going to be introduced because of this, but we will use it with other functions as well. And we will make this available in the next release of Dyalog. beyond that, we may have to work on further enhancements for processing APL source. Thank you very much.